Hello everyone, and welcome to the first video of a new series about working on the project of my own functioning GLaDOS miniature. I already uploaded 3 videos about this project and I want to quickly recap those. The videos are all linked in the description below. The first video was an overview about the time span in which I worked on the project. The result was shown in a small video at the end, showing that GLaDOS can move and respond to voice commands. The second video was a complete breakdown of the hard and software of the whole system. There, I showed how I got the body to move, the communication between the body and a separate device working, and how the used program for voice recognition worked. The third video showed a portal radio that can be used as a speaker. In my case, this replaces the Bluetooth speaker used previously for the sound output of the program for GLaDOS. This video will show the start of the complete makeover of the program used for GLaDOS. Here, the goal will be to create a plan for the program in form of a UML diagram. The core of the planned components will be implemented and tested to act as a foundation for all other future components. The first and hopefully obvious requirement is the overall physical system. This is a given for me, but if someone wants to replicate this project, the video of the technical overview should be visited first. The second requirement is the decision about the used programming language. I chose Java mainly because I am most fluent and comfortable in this language. The third requirement is to narrow down what features should be planned and implemented in this video. Here, I decided that nearly no functionality from the old program will be implemented. Instead, I will create the foundation for all other components to build upon. This is based on several tests I did regarding the usage of multiple threads and a modular component system. This should allow easy communication between individual software components and should make the addition of new components fairly easy. All other components that are planned in this video will be implemented as empty components without any functionality. With the requirements covered, the design of concept will now follow. In the first video of GLaDOS about the timeline of events, I mentioned a big plan for a new program. This program was called Aperture Automation Science, but thanks to a suggestion of the viewer, I changed the name to Aperture Automated Science, or short, AS. Some might have noticed that I used 2 different voices for sound output. The first one is obviously GLaDOS, but I wasn't content with just one. I decided to add the voice of Otto from the movie Wall-E as a second one. This ultimately led to the decision to split up the overall planned program into 2 sections. The first section will be called Facility Management and will be controlled by GLaDOS. Software components of this section include Device Management or Network Management. The second section will be called Data Management and will be controlled by Otto. Software components of this section include File Management, ID management or data mining. This means that the single program called AAS will be split into multiple components. The first 2 components are GLaDOS and Auto for the 2 different sections. In addition, there will be 3 more components to achieve all desired features and functionalities. These include voice recognition and sound output as 2 components, and a so-called Action Queue Manager as the last component. These 3 components will work separate from GLaDOS and Auto, as they realize a functionality that both sections will need. With a broad explanation of the overall plan, the question of what the Action Queue Manager does should be answered now. For realizing communication between software components and individual threads, a thread-safe solution is required. For this, I came up with the so-called Action System. This system mainly consists of a thread-safe list in the Action Queue Manager, a container class, and many references to the one list in each software component. Before further explanation, the definition of an action is required. An action is something that needs to be processed by a specific software component. The source and destination of each action is known, and an option exists to wait for the execution of an action. Since every software component has its own ID, which by the way can be simply assigned via a file where each class name and corresponding number is included, an action can be traced to each source and destination. This information is stored in the container class, along with the action itself. All actions are stored in the list of the Action Queue Manager and are processed based on the first in, first out principle. The Action Queue Manager periodically checks if a new action is present in the list and will call the corresponding software component to handle the event. This means that while every component has a reference of the entire action list, they can only add to it. The removal of actions can only be done by the Action Queue Manager. With these plans in mind, a corresponding UML diagram was created. As you can see, it is quite more complex than what I explained, but I don't want to bore with more details and get to the realization. The realization of the UML will be done, as said previously, without any features from the previous program. This means that after realization, the whole system by itself will not be really usable, but it should be sufficient for first tests. The UML is implemented in Java version 8 using the IntelliJ IDE by JetBrains. If you are interested in the specifics of the code, you can check out the GitHub link in the description below. With the coding out of the way, let me define and do some tests and a demonstration. As already said, due to the implemented features, or rather the lack of, this chapter will be rather short because there's not much to show. The tests will be done in the terminal of the IDE since there isn't any other way implemented. The first test is the start of the program. At startup, the program reads in the component IDs for each software component from a file. These IDs are then given to all components, which is visible as temporary prints to the terminal. The last two prints to the terminal, which show the command for listing all other available commands for using the terminal and a statement that the program finished its initialization. The last print was already generated over the action queue system, where the action queue manager sent this action to the terminal handler. With this, the startup of the program is completed. As there are not really other components implemented, there are two threads active. One thread is for the action queue system, and the other thread waits for input via the terminal. The second test will use the available commands for using the terminal as an interface. First, the available commands are printed with the before mentioned command. This prints out a short list of available commands. This list will of course grow as other software components will be implemented. For this test, the last command should be used. This command acts as a refresh for the component list, where the contents of the component list file is read again. Typing this command into the terminal results in two prints from the program. The first print is a confirmation that the command was received. The second print indicates that the component list was read. The terminal now waits for commands again. This test shows that using the terminal is possible to control any other component of the program, given that the commands are implemented in the terminal manager. The last test that will be performed is shutting down the program. As there are, or rather will be, many threads simultaneously in the program, the whole thing should be shut down properly. When giving the shutdown command to the terminal, an action is sent to the action queue manager. This manager sends actions to all subcomponents to shut them down. In the case of GLaDOS, this action is forwarded to the terminal manager to shut down the thread for terminal inputs. All subcomponents then set back a confirmation. When all subcomponents are shut down, the action queue manager sends a last print to the terminal and then shuts itself down. As you can see, when I give the shutdown command to the terminal, the system reacts as expected and the program shuts down. This functionality is important to avoid keeping some threads running in the background. Also, the shutdown via an action means that the same functionality can be easily implemented in other components, for example the voice recognition module. This makes future additions much more easy. With the tests done, I want to quickly sum up everything that was covered in this video. First, requirements were set on how the program for GLaDOS should be reworked and which components should be implemented in this video. After that, the new systems to achieve the goal were explained. The realization led to small tests to show that the system works, but is not really useful for GLaDOS. Regardless, this implementation proves as a very important foundation for all upcoming editions. Since I planned a lot of different functionalities for this program, I thought that a visual representation of the overall progress would be nice. I decided to visualize the progress in form of a skill tree, where individual nodes represent one feature. With the end of this video, the first node is finished. This node represents the overall framework for the new program without any actual functionality. I currently plan on covering one node in each upcoming video, so you can follow along better in shorter videos. It's been some time since the last video, and I want to quickly go over some things before this video ends. First up, I changed the general structure of this video compared to the previous ones. In addition to this, I decided to not go into too much detail. Both of these decisions enable me to make shorter videos, which show about the same content. For those who are interested, I always publish my code and link to it in the description. I would appreciate if you leave feedback for this updated approach, since this gives me the chance to further adjust or just experiment with some things about the video. Thanks for watching!